We're on. Hey, if you're talking now, you're getting recorded. Everybody on the internet will know. No, just kidding. Just kidding. Hey, all right, let's get into lecture. I know it stinks to have a class that actually lectures in the beginning, but I insist on teaching you this, and dang it, I'm going to make sure I do. So here goes, all right? These are the slides. You're welcome to take notes on the papers I gave you, or however you like. Let's see here. So, we already talked about the syllabus, but what we're going to do here in this class is talk a little bit about the prerequisites that we use to build up to SEM. So I have an example with data. Actually, it's a contrived example and made up data, but you know, that's okay, right? My field is the only field in science I think we get away with making up data. So we do that a lot. But it's going to cover an ANOVA regression, essentially, concepts from construct measurement, so what do we do with reliability, essentially, and then why do we want to use SEM in the first place. And then at the end of class, I'll have a brief introduction to R, and I'll get you started on that, mainly with the syntax starter file for the homework that's due in 2 weeks. And the data to show you how to work with that. And then I would strongly encourage you to get on downloading R and putting it on your machine. My experience with R is sometimes there's these little quirks from different computers and different things that make it harder to install for whatever reason, although it's nothing. It's very easy compared to, let's say, SAS, which is ridiculous. So what I'm going to do this semester that I haven't done before is I like to come up with a few key questions talk about during the lecture. Kind of these are the big picture topics, and these are the questions for today. At the end of the lecture, we'll revisit those, and you'll have a chance to kind of try to bring it back together, hoping that'll make it synthesize with what we're talking about. It also helps keep me reined in. I like to go off on tangents, and hopefully this will keep me on topic a little bit more. So, what these questions are for today. Number one, what is structural equation modeling? What? How does it differ from linear models? Or how do, grammar on the third slide, how do structural equation models differ from linear models? What other models or methods are structural equation models related to? And why would you use structural equation? Seems very straightforward, I hope. So we're going to take, and to kind of discuss this, we're going to take data from 150 participants in the study that's simulated, but they provided self-reports of a 5-item happiness scale. There's a 5-item happiness scale that's fairly commonly used called the satisfaction with life scale or subjective well-being, and it's become a cottage industry that if you're satisfied, you could put take the word life off and put something else there. Satisfaction with your course, satisfaction with whatever else. I mean, who knows? Anyway, this is sort of what it's supposed to be. And I also took a person's marital status. By the way, I picked marital status because I was looking for a dichotomous thing. And this is not meant to be a treatise on my opinions on marital status and happiness. All right? So let's just leave that alone. I'm just looking for a simple little study to talk about how it works. So, each participant responded to one survey. What does that mean? Anyway, they took a 5-item happiness survey where items were essentially 5 questions, and you had to rate it with a 5-point, what's called a Likert scale. So it's like strongly disagree, I don't know, agree and strongly agree. And then there was a 1 marital status question, are you married? Yes or no? And the researchers who were doing this study were interested in the effects of marital status on happiness. Right? So if you were these researchers, would you think that marital status has an effect on happiness? Right? Yes? Is it have a positive effect? Do people married have a higher happiness than people not married, or is it a negative effect? So I see no effect. No effect? That depends on what your status of the marriage happens to be. See, I'm just not trying to be too much information, but you'll get to know me a little bit over the semester. I'm married now, and I was married once before. actually in Lawrence. I have a daughter who lives in Tuscaloosa. She was born in Lawrence. And so I can tell you it certainly depends. All right, marital status certainly depends for my own. But really, this is more me trying to make an example that shows you there might be more to data than meets the eye, and this is why we're going to use SEM. All right. Okay, so I simulated the data from R, but I saved the data as a CSV file, a comma delimited file itself. So if you're not familiar with simulated data, basically. We use a random number generator and a few statistical distributions, and voila, we get fake data. Took that data, saved it into a file. A CSV file is something called an ASCII or plain text file. You can download it from the internet. And if you were to open it up in a text editor, this is a text editor named TextPad, which is down. Let me get a laser pointer. Down right over here. This is TextPad right here. That is what it looks like. It's just text, plain text. And in between each entry is a comma. So each person is represented by a row of this file, and each variable or datum from a person is represented by a column. If you're in Windows and you download this file and double click it, and if you have Excel installed, it opens in Excel and it looks like a spreadsheet. So that's why I like this file. It's text, so it's easy to read into R. But it also opens up in a nice visual text spreadsheet as well. So you can find it online, and you can download it and put it into R. You can try it on your own, or you can look at the R syntax as well. So let's talk about the general linear model. Have you heard those terms before? General linear model. Yeah, that's good. I always love the statistical naming. All right. So someone thought. So here's my abbreviated version of history of statistics according to template. Right? It's only according to me. This is probably inaccurate or whatever else. But at first there was analysis of error. Excuse me. First there was linear regression. Right? You can see Gauss used linear regression at least in the 1800s at some point. And then there was analysis of variance, and that was popularized by Fisher in the early 1900s. And somewhere along the lines, people thought, wait a minute, these are pretty much the same thing. It just depends on what we put in for our predictors, whether they're continuous or quantitative, or they're somehow coded up as categories, zeros and ones. And they thought, oh, this is great. We're going to call it a linear model, but not just any linear model, the general linear model. And sure, wouldn't you know, then they made more discoveries in statistics that said, oh, wait, they can broaden this. And now there's models that are called generalized linear models. Those are models where outcomes might not just be quantitative in nature or may not be symmetric and quantitative, if you want to think about that. And we go even further, and SEM is part of something that's part of a field called generalized linear mixed models, where sometimes you may have things that are random in the linear model itself. So yeah, whoever thought general thought this is the be-all and end-all, that's it, and then the world kept spinning and people kept thinking, and we found out more things. And so it's kind of a misnamed thing now, but we'll keep calling it that. I just like to call these linear models, but it's an open regression, and that's where we're going to start, and we're going to add things to it as we go along. Here is the general linear model, though, is this broader picture of basically you have data, you have an outcome variable. So in our case, our outcome variable, think about it as being the happiness scale score. All right? Somebody's score for happiness. The higher the happiness scale score, the more happy this person thinks they are. The lower, the less happy they happen to be. And so that would be like our y. We'll call that y. I like to use y for a dependent variable. And we only have one of those, so we call that univariate. And if we were to try to predict this happiness using a categorical predictor, like we're going to do today, we would use the name ANOVA, analysis of variance, right? Bless you. If we had continuous predictors, perhaps we had amount of income or weekly paycheck or how many cash dollar bills you have in your pocket, that would be, we'd call that regression. We only did that. But if we put both together, then we have the word ANCOVA, analysis of covariance, sort of. If they interact, it goes, anyway. We start to run out of labels after a while, the point being. And this is where my philosophy in teaching this starts to be there. SEM is another set of labels that somehow broadly mean some sort of loosely associated topics, but I think more I like the nuts and bolts more than anything else. If you've taken multivariate yet, some of you have, some of you haven't. that's cool if you haven't, but I'm teaching this course as if you haven't. If you have more than one variable, maybe we have not only a person's happiness, but we have, let's say, their, I don't know, pick another thing we want to measure on a person. Openness to experience, maybe one of those personality traits. Let's do that. What's that? Lifespan. That's a good too. We have more than one thing we want to predict. That would be a multivariate model, and you'll see the letter M show up in front of ANOVA. It becomes MANOVA. What an acronym! What a naming process, right? And then you get to regression, and it's like regression. No. Multivariate regression, right? Or you could have MANCOVA, but the same thing happens. All these models get lumped under this umbrella because they typically assume that when you have this prediction equation, at the end of it, you're not going to predict, you're not going to predict everybody's score exactly correct. And so you have this error, how far off you happen to be, and we make an assumption in each of these models that error follows a very specific distribution. That error follows a normal or Gaussian distribution. This is kind of this bell curve, with some zero mean and some estimated variance around it. So how much variance depends on how accurate our predictors are. If we're very accurate, there will be very little error variance. All the errors will be very, very small. If we're very inaccurate, there'll be lots and lots. Right? So when you put both of those together, what we're saying the data happen to be is the conditional on what you're predicting the data with. The data are conditionally normal. Right? So once you look at that regression line, your prediction for a person happens to be the mean of everybody who have the same x's. That's the conditioning part. And their error for it happens to follow along it. So that's the big picture here. I mean, I say that because not always, sometimes you take stats classes and people are like, oh, data have to be normal, data have to be normal. And the data don't have to be normal. It's the conditional distribution that's normal. Right? And I'll tell you why. Well, we'll get into that. May get into it later. If not, you can come talk to me. So here is your conditional normal general linear model. We may have a Y for a person. I like to subscript things with labels. So P stands for person here. So it's person P's observation Y. And perhaps we're predicting it with a predictor X and a predictor Z and the interaction between X and Z. And so this is note the time the first equation of the semester showed up on the slide. All right, here we go, right? The first part of that is the regression line. This is beta 0 plus beta 1. This is beta 0 is an overall intercept. It's our predicted value when each of the predictors is equal to 0. Beta 1 is the increase in Y for a 1 unit increase in X when Z equals 0, because we have an interaction. Same thing with beta 2. Beta 2 is an increase in Y for every 1 unit increase in Z when X equals 0. And finally, beta 3 is the increase in Y for any 1 unit increase in the product of X and Z together. So that part over there in KU red, sort of looks like KU red, is what we sometimes call the model for the means. It really gives the mean of the conditional distribution of a person's data. It's predicted value is probably what you've heard it before in your regression course. Right? And so X, Y, X, and Z are only measured once per person. That's it. It's a univariate linear model here. Error, E, forms the backbone of what's sometimes called the model for the variance. Because we make this assumption that error follows a normal distribution. This is very cryptic down here. I'll describe this more in the slides to come and then actually next week. Error, this little tilde means is distributed as. And that N says normal, a normal distribution. A normal distribution has two parameters that describe it. A mean, right? Here, let me see here. Here's see how my drawing skills work, right? Normal distribution. Oh no, my pen isn't working. All right, never mind. Back to the chalkboard. If this is error for a person, this is the distribution that might follow. That's normal, sort of. It's like a bell curve. The middle of it, or the midpoint, the mean, is 0 in this case for error. That's the first term. And how spread out it happens to be, I like to draw it like this. That thing is measured by the error variance that comes from the model itself. Right? So we actually estimate that as part of our regression, or part of our ANOVA itself. And for every person, that variance is the same. It's some assumption called, I love this word, homoscedasticity. You can tell I've been teaching for a while. If you was teaching statistics, right? Homoscedasticity. If you can play that in Words with Friends, you're a freak. So, I see it. I see you looking. You're going to think about it. You can't fit that on the board. Yeah, no, I don't think so. So we're going to build a linear model for predicting a person's happiness. Right? And we're going to do this in a kind of an odd way, but I want to do that to introduce some more of the statistics to get the stat part of the brain flowing. You know how some people say left brain and right brain? Statistics is full-brained. All right? That's how I feel about it. Sorry. First of all, that left brain and right brain thing. One of my other things I love is neuroscience, and that's I don't really believe in that. It's neuroplasticity, but statistics is a full brain thing. All right, it's art and science and math put together. Anyway, sorry. I love what I do. So, if you have a 5-item scale for happiness, you want to come up with a happiness score. What do? Add the 5 numbers together for each person, right? Total of 25. And we're going to come up with that. We're going to call this variable happiness underscore sum score. That is called a sum score. It is just your score. How many of you have taken some type of measurement or psychometric class where you talk about that? I don't even know what the term is. What's 820? You took 821 last year? I'm looking at the REMS first year students. Is that what was it called? 22? 21? What? Measurement, scales, things like that. So this is that. All right, it's one of those. All right, so that's that. We are also going to code marital happiness with a 1 if the person's married and a 0 if the person is not married. We call this reference coding, if you remember from the linear models. We're actually not going to see this in a lot of structural equation models. We do up until we get into multiple group analyses, but it does exist. Sometimes we call it dummy coding. Brief side note, if you've taken my classes, you've heard this story before, but don't ever label a variable with dummy on it because you never know where you'll present it. This is dummy married, right? Again, sorry. I have a story about my advisor and his coding system for Native Americans that he presented a reservation once, and it's not a good one. So it's just lay off the word dummy in it. That's where reference comes in, right? So what we're going to start out with, though, is a model for the data. Now, a lot of times if you've taken ANOVA, we don't say there's an ANOVA model, but this really is a linear model. We're going to put in our data on the right-hand side of an equals, left-hand side of an equals, you're right. Right at my right, your left, this y equals, and we're going to say over on the left-hand, your right-hand side, that is equal to our predictor, something times our predictors, our linear model itself. And so the empty model is a model that's pretty stupid. I'll just say it. It's stupid. Pretty much all models are stupid. They're not living things. But this empty model has no predictors for happiness. So if I were to go to you and say, what would you think a predicted value for a person's happiness score would be if you had no predictors? All you had was the data. What would you use to predict a person's happiness? Probably I heard it mean. Probably the mean. Okay, and that's what's going to happen, right? So we're going to have that empty model, and then we're going to add to it our marital status predictor. I did this in a package in R that we're going to use this year called LaVAN. LaVAN stands for Latent Variable Analysis, LAVAAN. And we're going to get very familiar with that. But our linear model's up top here. Y, so that YP is a person's happiness scale, sum score. It's going to be equal to an overall fixed intercept and some error, and we're going to say error follows this normal distribution with error variance to it. So we end up having 2 things we get estimated from this empty model. We have the mean, or the intercept, which is our person's predicted value, and that happens to be 8.813, and sure enough, that is the actual sample mean for the data. If you go and grab the mean itself, it is 8.813. Isn't that cool? Even though this is a regression analysis, there's the mean. Hey, it's my way of connecting data to analyses, models, right? Sigma squared error here is our residual or error variance. I like to call it error variance. Since SEM, there's a lot of things called residual, which is a terrible word. I've been trying to think about statistics in our jargon recently, and it's all terrible. We don't have a good marketing thing. So like if you think of the word residual, if you weren't in the stats class, what does that mean to you? Nothing good, right? Or variance. Sometimes we decompose variance. What's decompose mean to you? Anyway, it's terrible. This is our variance. This actually turns out to be the variance of our data. If we were to take the sample variance of our data, we'd find it was 3.535. Now remember, variance is something we don't often talk about. We more often talk about data with standard deviation. Variance is the squared standard deviation, just to remind you. But in statistics, and in particular in structural equation modeling, we talk about variances almost exclusively. We rarely talk about standard deviations. So mainly because it fits with this. When we get to a multivariate model, it'll fit better in there. How are we doing? Cool. So, as there are no predicted values in the model, each person's predicted value is given by the intercept, and that's the mean. In fact, here's our code to give you the mean. Sorry that this is so small. You asked for the mean of the happiness for the data. It's 8.81. If you ask for the variance, it's 3.559. Believe it or not, it's close to the same thing. It's not quite because of right here. Remember there were two types of variances that existed in statistics. If you remember your first stat class, started doing standard deviation. There was a formula that had n and the formula that had n minus 1. I don't want you to remember formulas, by the way. Bless you. Bless you. Can't let the sneezes go unrecognized. Maybe we can use a different term for it. Anyway, no. So it's a central concept in what we do in statistics, and it's not just variance of data. Everything can have variance. Anything that's sampled has a variance. But the variance happens to be, if you think about it, here's the formula. It's there are two formulas. Something that's divided by n minus 1, something divided by n, but this part of it on the right is the same. It's a person's observation minus the mean. Right? So it's how far off they are from the mean squared. And we're summing this over all people. Now, if we look at this bottom formula where we're dividing it by n, that's like saying, if you remember the sample mean, it was the sum of y over n. Right? That was the average score. This is then the average squared deviation from the mean. Right? This is saying the variance of this estimate with n is how far off on average a person is from the mean squared. Right? And it's in the number of units of the variable. So if this variance of, so it's the number of units squared. Get to that in just a moment. So actually, let's think about it. For happiness, it's 3.55 or thereabouts. That meant that the mean was 8.81. So it means on average each person was 3.55 squared units away from the mean. Squared happiness points. Right? So it's squared points. It's kind of like the idea of the concept of area, right? The number of area, the square inches in this square of floor here, you can't just describe it as 15 inches or whatever. It's 15 inches by inches. It's inches squared. That same concept of scale, that same concept of units follows with us here with variance, squared variance. Ironically, if you took the square root of this, you're back down to points, not points squared describing this. How far off, how many points away from the mean a person would be on average is the standard deviation. Right? So there are two formulas. The first one, n minus 1, you may have heard is unbiased, which again, another statistics term, right? Whereas the 1 by n is biased, right? So it's like, oh, where do you hear biased? I always hear it with like Fox News or MSNBC, right? This is like your bias. I don't want to, I'm not over here to make a political statement in stats course. In fact, I'm going to keep you guessing as to who I write in my candidates all the time. They're always my friends. But anyway, this is biased, meaning that in the long run, if you use this, the true standard deviation, it will not hit. It'll be somewhere off of it. Right? So that's where we can make it unbiased by dividing by 1. But that bottom one exists, and it still exists for a good reason. It's because when we use a certain class of statistics to get our results, the thing that gave us the numbers right here, these numbers, is an estimation method called maximum likelihood that we're going to talk about in the next couple weeks. And that biased value right here comes about as a maximum likelihood estimate. But there are other, so it's biased, but there are some other really good things about it, right? It's kind of like saying, yeah, I watch Fox News. It's biased, but they have really good weather, right? Or I watch, if you're not there, I watch MSNBC. You know, it's biased, but there's really good commercials or something like that. I don't know. I don't even pay for TV. That's how lame I am, right? So if you're thinking I'm watching Fox News or MSNBC, anyway. So that's what I just said this right here. Actually, I didn't say this right here. Standard deviation and variance, we just talked about it with data, but it could also mean the same thing in terms of any statistical quantity or parameter. Right, so you think of the mean itself, the sample mean. Right? Here's your sample mean right here, 8.813. What is the number in parentheses beside it? That it's standard error, it's called, right? The standard error is the standard deviation of the mean. Which means if you were to repeat this sample over and over and over and over again and just write down the means and then take the standard deviation of what you wrote down, it would be that. Right? And actually, believe it or not, that number is this divided by, or this, the square root of this divided by n. So it does have a connection. But here's a number for you. What is 0.408 for the variance? Standard error for the variance. Have you heard of that before? The variance has a standard error. Right? If the same thing happens. If you were to do this study over and over again, right, this is how much the standard deviation of all your variances would be. And that's kind of underscoring the point. Every statistical parameter that we have, every model term that we're going to estimate will have a standard error with it. Sometimes they're not useful. In fact, if you were just doing this in the regression package in SPSS or SAS or even in R, you wouldn't get this number right here. It wouldn't show it to you. And this variance itself would be buried in some analysis of variance table as the mean square error. But I want you to think more broadly than that. To SEM, each of these terms still exist, and all of them have standard deviations. Where those come from, where the standard errors come from, they come from maximum likelihood. They have certain properties of maximum likelihood that give us those numbers. So, how we doing? So exciting. Does this make you remember statistics, though? It's been a long break. I didn't do any statistics. Well, no, I did. Sorry. I do statistics every day. That's what I always tell the people who aren't in statistics. It's like 24/7 for me. And I'm married to someone who does statistics also. So it's like not only 24/7, it's like dinner and breakfast and lunch. Anyway, as my spouse goes into labor, that will be we're actually, the plan for trying to keep her away from the pain or trying to get through the pain is to talk about statistics. I kid you not. A baby's room is decorated with distributions. No. I'm going too far. Not quite. So this is saying if we have the variance estimate right here, this is one of the reasons why we're not really concerned about n versus n minus 1. Anything that's biased can be made unbiased. Right, so here's the variance estimate from the Levon output, 3.55. And if you were to 3.535, and if you were to do it just from R with n minus, this is with n being the denominator. This is with n minus 1, 3.559. They're different. But you can take the one with n, or you can take the one with n minus 1 and switch the denominator, right? You can always multiply it by what it was and divide by what you want it to be. So we could take this thing, right, or we take the date, we could take the thing that comes out of R we multiply it by, this is R's code for n minus 1, and then divide by n, we get the biased version. That's like, I don't know, taking the BBC account of our election, and no, never mind. Everything's biased, right? There's always a bias. Anyway, there it is. All right, so that's great. That's fun. What happens when we put in married, our status, marital status, right? So when I code up these reference or dummy coded variables, I like to put the label of the variable as my predictor. This married P is a 1 if a person's married, and a 0 otherwise. So now we get more of a model that does something, right? How do we interpret each of these results? The intercept that we estimated was 8.471. What does it mean?
The mean of the non-married.
That's right. That is the mean happiness of somebody who is not married. Okay? And that is because beta 0 is always the predicted value when all the predictors are equal to 0. And we know, because we coded it, married is equal to 0 for somebody who's not married. Cool. What is beta 1 then? If we use the typical regression analogy, it would be how much happiness goes up for every 1 unit of married. Okay. I know what you're thinking. There's a joke in there somewhere, and I'm not going to make it. That would be the difference, because we have only two groups. The people with the 1 versus the people with the 0. There's only the 1 unit increase in marriage is kind of a misnomer when we've coded our variable, right? A 1, people who are married. So literally, people who are married have a mean happiness that's 0.744 points higher than people who are non-married. Okay. So far, so good? Finally, sigma squared error, 3.398 is the value. Is that bigger or less than the sigma squared error from the previous slide? What was the previous slide? Yeah, it's 3.535. It's smaller, and it's smaller because we've explained some of that variability. Okay? It's shrunken. And the proportion of the variability explained, we could actually compute. We could say, oh, we know what the last version was, we know what the current version is, we get their difference. And if we divide it by what it was before, that's actually the proportion of the variance explained. That's R squared. We can come up with a value for how much variance is explained. So here is the labels that go with each of these. One thing I wanted to note, if you had more than one marital status, if you wanted to include people who were, you know, if you go to the doctor, I always wonder why they put this. Are you married? Are you single? They put divorced there too. It's like when I was divorced, do I check both? Anyway, you know, there's more one thing. So if we had more than one status, we want to put divorced. What we would do is instead of having a 0, 1, 2, we would actually have another coded variable, right? So we'd pick one group, maybe it's non-married, maybe it's people who've never been married, and we would have a variable that if you're currently married, it would be a 1, and a 0 if you're not married, and we'd have another variable that would be if you're previously married but not currently, it would be a 1 and 0 otherwise. So it's always 1s and 0s in these variables that we're creating, but then we put more than one predictor into the analysis itself. So that is the description, the text description of our intercept. There's our text description of our slope. And here is kind of an interesting thing. If you have run a model, if you wanted to say, oh, okay, I just coded married as 1 and non-married as a 0, if you flip that around, right, that's fairly arbitrary, right? I don't have to code up married as being a 1. I can say non-married as a 1. The model is identical. The only thing that differs is your estimates a little bit, right? So here, we can also get all means back. So if we look here, what is the mean happiness for somebody who is married? It's the intercept plus the slope. It's the predicted value. That's 9.215, and the predicted happiness for non-married people is 8.471. So we can get both of those means back. Had you coded things differently, though, Right? Had we coded it with non-married equals 1, what would beta 0 be? What was that? It would be larger, but which number would it be? It would be 9.215, right? It's the mean of the reference group. And so beta 1 it would be a negative 0.744. So really what we're doing, if you want to talk about are married people more happy than non-married people, you could still get to that answer. And the coding is just arbitrary. That used to blow my mind. And really, you can just code it, and yeah, it's pretty arbitrary. So, back to the big question, the big picture. How do we determine if married people are more happy than non-married people? Or different happy? I would just say different happy. Say more. We could use a hypothesis test. Oh gosh, here we go. Hypothesis testing, really? First day? Terrible. All right. If we were to ask the question, are married people different in their mean happiness than non-married people, really what we're doing is framing this hypothesis statistically. If beta 1 equals 0, that's our null, actually, the null hypothesis, or H0, is that beta 1 equals 0. The alternative is that beta 1 is not equal to 0. So, if we were in an ANOVA table, in an ANOVA class, we look at our F test in our ANOVA table for this F and a p-value, and if p is really small, we would reject the alternative. We would reject the null hypothesis, and we would say this can't be the case, so they must be not equal to each other. But in SEM and in most other techniques that use maximum likelihood, which is pretty much everything once you get past that first year statistics sequence in grad school, you don't get an F table. Right? You don't have it, so where's your p-value? It comes, actually, on the line itself. You may have seen this in the estimates table in some regression analyses. But what ends up happening is here's your estimate. This is the slope for happiness. You can barely see it. It's 0.744. You have its standard error. And if you take the estimate divided by the standard error, you get a number, 2.462, that is actually what we call a Wald test, which uses a z, or normal distribution. In regression and ANOVA, you may see t. We could use t there too. It's kind of a finite sample thing, but in the SEM packages, they tend to ignore that. Depending on which regression and ANOVA package you use, it's also ignored. They're essentially the same thing. So 2.462 we could compare with a standard normal, or z distribution, and get a p-value of 0.014. So it's pretty small. I'm going to arbitrarily set today's type 1 error rate to 0.05. Remember that? So if this is less than 0.05, we reject. So what do we conclude? There is a mean difference between married and non-married people in happiness. Saw that one coming, didn't you? Or did you? So, one last thing to interpret the residual variance. This is what I was talking about briefly before. You notice we had two models there. Model 0 we never really do in a regression class, but in a lot of the multivariate and SCM-based things, sometimes we need an empty model to make comparisons. One of the things we need is R squared. How much variation in happiness does being married account for? For Model 1, the variance estimate was 3.535. For Model 2, the variance estimate was 3.398. So if we take the difference of these two and divide it by what the bigger value was, we see that 0.039 is our R squared. Is that R squared very big? It's how much, R squared is it's the proportion of variance accounted for by being married. Is it big? Not really. 0.039. Believe it or not, that's sort of the size of many effects that we see, actually. Probably a little bit less than that. Maybe a little bit bigger, but it's not very big. It's 4%. Marital status explains 4% of the variation in happiness. So that's what ends up happening. So when you put a predictor in the model, variation of the variable gets explained or shrunken. Everything going well? Time for some BlissText. Questions? How many of you are thinking, what have I gotten myself back into? No? Good? All right. I'm thinking that. No, I'm just kidding. This is one of my favorite classes to teach, actually. I am fortunate to be able to teach it. So one thing you may or may not have heard of before, we're going to cover this a lot more when we get to path analysis, though, is something called standardized coefficients. Right? A lot of times, if you're doing a regression analysis, you have a quantitative variable or some coded variable in X, and you'll have some quantitative variable in Y, and you can interpret the regression coefficient as, for 1 unit of X, as X goes up 1 unit, Y goes up beta 1 units, right? But what if you have lots of Ys or lots of betas or lots of everything else? So, for instance, if I put in this, if I had another model and I said, oh, my beta 1 is 0.8, right? As this unexplained variable goes up 1 unit, Y goes up 0.8. That looks to be more, in terms of direct units, than 0.744 that we observed here in our analysis. One of the ways that we can try to compare the effect of variables, independent variables, on dependent variables is to create something called a standardized coefficient. Standardized is the way of taking units out of the equation. Right? So here it's kind of weird for our analysis since we have a coded categorical variable present, but if you think about it, what beta happens to be, beta 1 here, this term right here, beta 1, is described in units of Y per units of X, right? Just like you would any type of rate. Like if you're familiar with chemistry, like you can have something per something else, right? What we need to do to take beta 1, that is what we call unstandardized. It's units of Y per units of X. But if we wanted to talk about it where we didn't have the units in the way, or if we could make it so that units were comparable, what we could do is take the units off of the measure itself, right? So beta 1, this is described as units of happiness over units of married. Now, again, you're going to have to bear with me here because it's 0, 1. It's not. We don't really have units. It's just 1 or a 0. But let's just pretend for a second. If we wanted to get rid of this, we want to take beta 1. We would be, if we wanted to think of this ratio, we could actually somehow multiply units of married over units of happiness, and perhaps cancel these out. And that's what a standardized coefficient does. So if we wanted to come up with a standardized coefficient for Y, we would have to figure out what the units of each of these are. Units, though, are based on standard deviations. It's our unit of measure. Right? So points of happiness. 1 standard deviation or whatever is 1 unit of that, you can think of. So if we were to take Y, or take beta 1, and here is units of happiness, this is Y. If we were to divide it by the standard deviation of Y, it no longer is the units of Y that goes up for every unit of marriage. It's now the standard deviations of Y that increase for every for every unit of marriage, right? Same thing with the denominator. We could multiply it by standard deviation of married, although we wouldn't because it's categorical. Anyway, point being, this is something that we may not have talked about a whole lot in regression course before, but it does come up quite a bit in SEM world, particularly when we get to path analysis. Path analysis is where we have not just one regression, we have a set of regressions simultaneously. So we'll have happiness, we'll have outgoing, we'll have neuroticism, we'll have all this, and some of those will be some of those dependent variables will predict each other, kind of all simultaneously. And so a lot of times you'll want to say how many, you want to start to compare values, but each of these variables may have a different scale, a different set of units to them. So you'll have to kind of take a standardized coefficient to get rid of their units. This is a clunky way of describing it, but we can also get those themselves. So how are we doing? About 10 minutes till break. Questions? Yeah.
If you can repeat when you use the unit, when you use the
It depends. Most often, you'll see, depends on your field actually, but more often than not, when you get into most of structural equation modeling, standardized units are used in terms of displaying output. So if you pick up a journal article, and in part of it, maybe you have a confirmatory factor analysis and something predicting a variable, those terms that are like regression slopes, they're called factor loadings, will be the standardized version that gets recorded. And for that reason, because the scale is sensitive to the number of standard deviations of what you're measuring. Good question. But we will talk about this at length in a couple weeks. I think it's actually week 4, perhaps even week 5. And then it'll show up every week afterwards. What's the standardized units? What's standardized units? What's standardized units? Okay. So, all that was great. But then, maybe you remember that in the linear models world, we assumed that the variables that were part of that equation were measured without error, right? What's error? Measurement error? Have you heard of this? If you have a scale, the scale is built, like ours, happiness, it was built to try to measure a concept that we can't directly see, somebody's happiness. And so when we do that, our measure may have what's called measurement error. A lot of times we describe measurement error in terms of the reliability of an instrument. Right? So how reliable was that instrument in the first place? And believe it or not, if you put something in an analysis of variance or regression, some type of linear model, in Y or in X, that has measurement error, the results might be wrong. They may have mentioned this, they probably mentioned this in your linear models course, certainly did, but then kind of went on their way, and that's what most people do research with. But sure enough, measurement error